Hey guys, and welcome back to another science lesson. We're here to continue on with our energy unit. It's called Making Energy, and we're going to talk about renewable and non-renewable energy sources. Stuff you might find in the news, so to speak. So let's take a look at our agenda today. A little bit of review, talk about some energy sources. Let's start with an example. Okay, how is electrical energy generated in the first place? Where does it come from? When you turn on the lights, where did that come from? Because it wasn't always electricity. So I'm going to show you how energy can be transformed to create electricity.
Here's a question for you. How many people does it take to turn on a light bulb? The answer seems simple. Just walk into a dark room, flip a switch, and instantly you can see, right? Well, the truth is there's a lot more to generating and delivering electrical power than you've probably imagined. Hi, I'm Lee Patrick Sullivan with Energy Now, and this Energy 101 video explains the system used to generate electricity. And it also explains what it really takes to turn on a light bulb. In order to understand energy, we first need to start at the source, literally. Mother Nature provides the natural resource we use to generate power. From natural gas to coal, ocean tides to mountain winds, the energy we need to create electricity must first be mined, harnessed, or collected from the earth. Some of these resources are finite, including fossil fuels like coal and oil, but others are unlimited, like solar or wind power. But a lump of coal or a strong breeze alone won't create the power that turns on your light. For every energy source, a chemical or mechanical process is required to turn it into usable electricity. Every day, researchers work to find innovative ways to use our limited resources, process raw materials, harness renewables more efficiently, and find entirely new energy sources. Today, the majority of America's electricity comes from thermal power plants. Fuels like coal, natural gas, biomass, and uranium are used to heat water until it produces steam, which powers a turbine and generates electricity. That steam turns propeller-like blades around a rotor inside the turbine. This turning rotor connects to a main shaft, which spins magnets with a coil inside a generator. It's the generator inside a turbine that converts mechanical energy into electric energy and creates electricity. Steam is an efficient method of producing electricity because the water can be recycled and reused as it changes back and forth between liquid and gaseous states. Transporting electricity from the power plant to your home is an entirely different process. Current technology cannot cost-effectively store large amounts of electricity, so significant challenges exist when it comes to transferring that electricity across long distances. Just enough electricity has to be generated to meet demand at all times and be transmitted through power lines to reach your light switch. Too much or too little power can crash the transmission system and cause a blackout. That's why a complex mix of logistics, management, and infrastructure is needed to transmit electricity from power generators to consumers. Enter the electricity grid, also known as simply the grid. The North American electricity grid is actually made of 4 large grid systems: the Western grid, the Eastern grid, the Texas grid, and a grid covering the Canadian province of Quebec. These independent regional networks of power plants and transmission lines carry electric energy at high voltage within their area to local utilities. There are very limited links between the 4 grids, which means electricity generated from a wind turbine in West Texas cannot reach an apartment building in New York City. For electricity to move through one of the 4 grids, its voltage must first be increased by a device called a transformer. Then the electricity can travel long distances across high-voltage transmission lines. These high-voltage lines are generally strung between giant metal towers. They stretch for miles from power plants to local substations in each neighborhood. You've probably seen substations along the side of the road and wonder what they do. Well, their job is stepping down electric voltages from levels as high as 765,000 volts closer to the 110 volts you use in your home. The electricity from the power line on your street passes through another transformer, which steps down the voltage once more, and then it travels along the line into your house. From there, the electricity enters your breaker box, and it is then distributed to light sockets and outlets. All you have to do is flip a switch. So, as you can see, from the raw materials to the power lines on your street, there's so much more to the electricity ecosystem than meets the eye.
So as you can see, there's quite a bit to electrical generation, and you might find a lot about it in the news. Let's go ahead and take a look inside of our energy unit packet, and we're going to look at this page called Introduction to Energy Worksheet. I want you guys to take about 5 minutes to pause the video and go ahead and do your Introduction to Energy Worksheet. Use the notes that you know so far. Please pause the video and return back in about 5 minutes. All right, we're back, and we're going to go over some of the answers to the Introduction to Energy worksheet in your packet. The two basic types of energy are kinetic and potential, or both. Now, a lot of them, of course, could be both, but they ask you to do the best match. But what's the main example about? So, a skier at the top of the mountain. Being at the top of the mountain, I would gather that they have lots of potential energy, the ability to possibly go down the mountain. That's your potential. Gasoline in a storage tank, that's potential because it's not in motion, nothing's happening, it's not being used, it's just being stored. Stored energy is also what we call potential. A race car, traveling at its maximum speed, kinetic energy, it is moving. The energy of motion is kinetic. All right, how you doing so far? Okay, look at this, number 4, water flowing from a waterfall before it hits the pond below. This is an example of both forms of energy because the water is flowing, and they're also giving you a little more information. Before it hits the pond below means it has that potential to do so. It's like the energy of moving water. A spring in a pinball machine before it's released. Okay, we've stored up the energy, therefore we have potential energy. Burning a match. The burning is in motion, in action. The thing is happening, so we're going to say that's kinetic. A match that's, not been lit could be considered potential. Running, refrigerator motor that's running is in motion. Okay, let's go ahead and have you finish the next part, and then we'll check the answers. All right, let's see what we have to do here. Determine the type of energy for each form, kinetic, potential, or both, and give an example. So mechanical energy, like something like maybe a roller coaster would be a good example. An object's movement, creates energy. So I'm going to say both because we know that kinetic energy plus potential energy gives you mechanical energy. That's basically the definition. Thermal energy, the vibration and movement of molecules. Because it's movement, it's kinetic energy. An example could be a fire. Radiant energy, electromagnetic waves. This is the electromagnetic spectrum. This is the energy moving in, as we might say, light. That's in motion. So those are kinetic energy examples. Electrical energy, we just saw. Movement of electrons. Again, movement of electrical charge. So anytime we're seeing movement, we're talking kinetic. Chemical energy, stored in bonds of atoms. Stored, okay, potential. When you see stored, it's potential. Nuclear energy, we know it's in the nucleus of an atom, and it's stored, then released when it splits. So I've got stored and released here, so I'm going to do both. Like your uranium atom has the ability to split into two smaller atoms, releasing energy, and when it does so, it's in action. Sound energy. Vibration of waves. Now this is a different kind of wave from the electromagnetic. Vibration of these waves actually does move the molecules of air, or sound can travel through solids or even liquids. That is a motion of molecules. That is kinetic. Gravitational energy, which really is an old-fashioned way of saying potential energy, it's the energy of position. So that's the definition of potential energy. So let's look at some examples. A roller coaster would be good mechanical energy. You could have a burning piece of paper or something for thermal energy. Radiant energy could be coming from a light bulb or some source of light. The sun releases not only light, but it also releases X-rays and radio waves and all different kinds of waves in the electromagnetic spectrum. Electrical energy, obviously, the movement of electrons through a wire in any kind of electrical device. Chemical energy, you could say it's in a battery. Nuclear energy is in a large atom like uranium. Sound energy could be a drum being hit, the movement and vibration of that. And gravitational energy, a skier at the top of the mountain or something like it. All right, guys, we have a couple of energy sources for you to put into your notes packet, please. Let's start with non-renewable. Not renewable energy that comes from a source that takes more than 100 years to replace, often known as fossil fuels. We're talking about oil, natural gas, coal, and things like that. Actually, the process of fossilization created these. These are the remains of plants and animals that lived millions of years ago that have been turned into their fossilized forms, which are coal, oil, natural gas, and we can distill different fuels from that. When burned, they release energy, just like if you burned a tree of today, it's similar. However, we're burning a more concentrated version of that in this form. So they're very good high in energy, but of course, it takes a lot to get them out of the ground. There could be pollution, and the burning of them releases a lot of CO2 and other pollutants. Fossil fuels are the main way we get energy today. There's a video on this. Please check it out in the folder to see a little bit more about where this comes from and the details. Fossil fuels can often lead to pollution, as you guys see here. Burning coal in power plants to create electricity can release different compounds into the atmosphere, which changes the pH or the acid-base balance of the rain, and we can actually do damage to our planet with these. So we have to be careful about how many fossil fuels we're using. One way that people get fossil fuels out of the ground is a method called fracking. Fracking is a way to remove fossil fuels by breaking or fracturing rock containing small pockets of natural gas, which is then collected. Let's take a look at some fracking.
What is hydraulic fracturing, or fracking? Since the Industrial Revolution, our energy consumption has risen unceasingly. The majority of this energy consumption is supplied by fossil fuels like coal or natural gas. Recently, there's been a lot of talk about a controversial method of extracting natural gas, hydraulic fracturing, or fracking. Put simply, fracking describes the recovery of natural gas from deep layers inside the earth. In this method, porous rock is fractured by the use of water, sand, and chemicals in order to release the enclosed natural gas. The technique of fracking has been known since the 1940s. Nonetheless, only in the last 10 years has there been quite a fracking boom, especially in the USA. This is because most conventional natural gas sources in America and on the European continent have been exhausted. Thus, prices for natural gas and other fuels are rising steadily. Significantly more complicated and expensive methods, like fracking, have now become attractive and profitable. In the meantime, fracking has already been used more than 1 million times in the USA alone. Over 60% of all new oil and gas wells are drilled by using fracking. Now, let's take a look at how fracking actually works. First, a shaft is drilled several hundred meters into the earth. From there, a horizontal hole is drilled into the gas-bearing layer of rock. Next, the fracking fluid is pumped into the ground using high-performance pumps. On average, the fluid consists of 8 million liters of water, which amounts to about the daily consumption of 65,000 people, plus several thousand tons of sand and about 200,000 liters of chemicals. The mixture penetrates into the rock layer and produces innumerable tiny cracks. The sand prevents the cracks from closing again. The chemicals perform various tasks. Among other things, they compress the water, kill off bacteria, or dissolve minerals. Next, the majority of the fracking fluid is pumped out again. And now the natural gas can be recovered. As soon as the gas source is exhausted, the drill hole is sealed. As a rule, the fracking fluid is pumped back into deep underground layers and sealed in there. However, fracking is also associated with several considerable risks. The primary risk consists in the contamination of drinking water sources. Fracking not only consumes large quantities of fresh water, but in addition the water is subsequently contaminated and is highly toxic. The contamination is so severe that the water cannot even be cleaned in a treatment plant. Even though the danger is known and theoretically could be managed, in the USA already sources have been contaminated due to negligence. No one yet knows how the enclosed water will behave in the future, since there have not yet been any long-term studies on the subject.
Okay, so as you can see, there are some problems with fracking. You're already starting out with trying to get the fossil fuel, and then there's other issues that you're doing. So, is fracking the solution to our energy woes? Maybe, maybe not. All right, let's move on to renewable energy. Energy that you can renew can be replaced within 100 years. Here's where we talk about the next generation, wind, solar, moving water, different ways of using the energy that exists around us to convert to electricity or other sources that we need. So lots of types of renewable energy: wind, of course, moving water, geothermal, which is heat trapped in the earth, biofuels, like things that we can grow in quicker than 100 years and quickly simply burn to get heat. Let's take a look at some different types of renewable energy.
Energy is all around us, a physical quantity that follows precise natural laws. Our universe has a finite amount of it. It's neither created nor destroyed, but can take different forms, such as kinetic or potential energy, with different properties and formulas to remember. For instance, an LED desk lamp's 6-watt bulb transfers 6 joules of light energy per second. But let's jump back up into space to look at our planet, its systems, and their energy flow. Earth's physical systems include the atmosphere, hydrosphere, lithosphere, and biosphere. Energy moves in and out of these systems, and during any energy transfer between them, some is lost to the surroundings as heat, light, sound, vibration, or movement. Our planet's energy comes from internal and external sources: geothermal energy from radioactive isotopes and rotational energy from the spinning of the Earth are internal sources of energy, while the sun is the major external source, driving certain systems like our weather and climate. Sunlight warms the surface and atmosphere in varying amounts, and this causes convection, producing winds and influencing ocean currents. Infrared radiation, radiating out from the warmed surface of the Earth, gets trapped by greenhouse gases and further affects the energy flow. The sun is also the major source of energy for organisms. Plants, algae, and cyanobacteria use sunlight to produce organic matter from carbon dioxide and water, powering the biosphere's food chains. We release this food energy using chemical reactions, like combustion and respiration. At each level in a food chain, some energy is stored in newly made chemical structures, but most is lost to the surroundings as heat, like your body heat, released by your digestion of food. Now, as plants are eaten by primary consumers, only about 10% of their total energy is passed on to the next level. Since energy can only flow in one direction in a food chain, from producers onto consumers and decomposers, an organism that eats lower on the food chain is more efficient than one higher up. So eating producers is the most efficient level at which an animal can get its energy. But without continual input of energy to those producers, mostly from sunlight, life on Earth as we know it would cease to exist. We humans, of course, spend our energy doing a lot of things besides eating. We travel, we build, we power all sorts of technology. To do all this, we use sources like fossil fuels, coal, oil, and natural gas, which contain energy that plants captured from sunlight long ago and stored in the form of carbon. When we burn fossil fuels in power plants, we release this stored energy to generate electricity. To generate electricity, heat from burning fossil fuels is used to power turbines that rotate magnets, which in turn create magnetic field changes relative to a coil of wire, causing electrons to be induced to flow in the wire. Modern civilization depends on our ability to keep powering that flow of electrons. Fortunately, we aren't limited to burning non-renewable fossil fuels to generate electricity. Electrons can also be induced to flow by direct interaction with light particles, which is how a solar cell operates. Other renewable energy sources, such as wind, water, geothermal, and biofuels, can also be used to generate electricity. Global demand for energy is increasing, but the planet has limited energy resources to access through a complex energy infrastructure. As populations rise alongside rates of industrialization and development, our energy decisions grow more and more important. Access to energy impacts health, education, political power, and socioeconomic status. If we improve our energy efficiency, we can use our natural resources more responsibly and improve quality of life for everyone.
So, renewable energies, geothermal, biomass, solar, hydroelectric, and wind are definitely an up-and-coming source of energy and perhaps giving us some of the best, most fuel efficient and cleanest ways to get energy. Well, guys, thanks so much for joining us on our latest Energy in the News update. Go ahead and continue on with that Energy in the News project by looking up a couple articles and making sure you're comparing two different kinds. You can see the directions in the Schoology folder. And hey, thanks for trying science, and we'll see you on the next one. Bye for now.